to cram for it over the weekend and over the course of next week if you don't have a lot going on. So far we've looked at problem solving video is a separate video. I'll try to make another problem solving video for the integrated rate law. Oh, did I upload the, let me take a look at YouTube and I'll get that all straight. There should be one problem solving video and then whatever the lectures are. And I was going to make another problem solving video for the integrated rate laws. Anyway, so our exam's on Wednesday of next week. It'll cover the stuff that we went over with solubility, and then it'll also cover this kinetic stuff. So today we'll knock out reaction mechanisms, and then we'll probably do, I need to talk to Lenko to make sure we're on the same page, but I'll probably knock out catalysts and reaction diagrams and stuff on Monday. That stuff's not so bad. But the stuff today can get a little bit confusing, and I'll explain why as I go through it. So, goodness, where to start here? So generally when we look at reactions, what we're looking at, or what you've seen up until now in terms of chemistry, is you're looking at the overall reaction. So for example, if we look at this reaction of, let me snap one from the book here. So if we look at the reaction, let's say this reaction, so we've got NO2, it's a gas. And we make some other gross gas that looks really deadly. But anyway, so this is the overall reaction, which we've just referred to as the reaction, and that's generally what it's referred to. It doesn't tell you the path between the reactants and the products. It just tells you I start out with reactants and I get products. The sort of path that you take there, so this is like if you're thinking in terms of a map, like if you're driving from Austin to Dallas, or let's say you're driving from Austin to Houston, since I'm more familiar with the routes. But like if you're driving from Austin to Houston, this is like I'm starting in Austin and I end up in Houston. What it doesn't tell you though is how I get between these 2 points. You know, did I take 290 to get from Austin to Houston, or did I take 71 to get from Austin to Houston? So the overall reaction just tells you where you start and where you end. There's something called the reaction mechanism. Let me move this. We'll refer back to this analogy in a minute. There's something called the reaction mechanism that actually tells you the path between those 2 points. And so for this one, it happens in 2 steps. So in the first step, one of these NO2 molecules combines with F2, which is kind of what we see happening here. But you'll notice that it doesn't. Well, we're not writing out the product here, which you form is an intermediate. So neither, well, this forms as a product, but this fluorine here is an intermediate, right? So we're not actually at the end of this reaction here. This is an intermediate step, or the first step in the series of steps from the reaction mechanism. And then in the second step, you produce NO2F. So this is the mechanism. Step 1, step 2. Let's call this like so these are our mechanistic steps, step 1 and step 2. If we sum these steps up, so if you add these steps up, just like when we did in thermodynamics, I don't know if you recall, but we do Hess's law or whatever, where you can kind of sum these things up and they cancel out. What we end up seeing is, so things on the product side will cancel out with things on the reactant side, just like in sort of algebra or whatever. What we see is that this thing adds up to be exactly what the overall reaction is. So I have one NO2, I combine it with another one, I end up with 2 NO2 plus F2 goes to 2 NO2F, because again, I sum these two up. And so we see that the reaction mechanism should sum up to the overall reaction. Oh yeah, sorry. Reaction mechanism is definitely the title. This is, so we're kind of deviating into that. Does everyone know what the elementary steps will be based on the reaction? Will those always be given? That is a good question. Let me circle back to that. That's an excellent question and kind of insight into what's happening here. Okay, so we've got the overall reaction. We have the mechanism. We know the mechanism must sum up to equal the overall reaction. There's a bunch of stuff that we can say about this. But so the key thing, or the kind of the analogy here then, is like from going to Austin, Houston, you know, I don't know, the reaction mechanism might be like, you know, step one, you get on I-35. And then step two is like, you know, I don't know, I-35 connects in, get on 71 or something. You know, but that's sort of the same idea here. So like the overall reaction, which is what we've been talking about, which describes a lot of things. Like, you know, if somebody's like, where are you going? You're like, I'm going to Houston. That's pretty useful information. But if they need more detail, they might say like, well, how are you getting there? It's like, okay, I'm getting on 35 and then I'm getting on 71 from 35. Does that make sense? Yeah, I think, no, this 30, it doesn't really matter. I don't know why I'm getting caught up in the details on that. But the same thing is true up here. It's saying, okay, like I know that I'm ultimately, if I mix NO2 and F2 together, I'm going to end up with NO2F. But how do I get there? And the answer is, you know, I start out with an NO2 molecule. So when in the mechanism, you can think about it in this terms. So in step one, an NO2 molecule collides with an F2 molecule. This collides with this and produces NO2F, and it spits out a fluorine atom. And then in step two, that fluorine atom collides with another NO2 and spits out an NO2F. So those are the actual steps that are happening. And in, you know, in real, like in a driving or whatever, you know, you're getting on 35 or you're getting on some street, in a reaction mechanism, the path, when we talk about like the actual path, it's not, we're not really talking about like a spatial type thing. We're talking about literal collisions between the molecules. So step one is this bumps into this and that produces a reaction. Step two is this bumps into this and that produces a reaction. So when we talk about paths in terms of reactions, we're talking about what molecules bump into one another. Okay. So to get back to what somebody asked, Tucker, so there's no way, well, is there a way to know the elementary steps based on the reaction, or will those always be given? So for you guys especially, there's no way that you would be able to posit a mechanism. Like, you know, if you're given this, you have no way to figure this out. Once you get a lot of experience as a chemist or whatever, you can start to propose mechanisms. Like you can kind of be like, this might be a reasonable mechanism, but even then you're still not really sure. The mechanism has to be experimentally confirmed. So for, let's say, mechanism, I don't know how to say that. Like a mechanism, yeah. Let's see, could you ask to be proposing a mechanism? No, I think for you guys, the mechanism will be given. Typically. Or like, there's a lot of different ways to ask these questions. Like we could give several mechanisms, for example. This would be a pain to write, but we could give several mechanisms, for example, in the rate law and ask you to figure out, you know, which mechanism fit the rate law data, that kind of stuff. But the mechanisms, like in terms of just writing out these steps and saying like how would you know that when NO2 and F2 comes together, a fluorine atom comes off? There's no way to really predict that unless you know a lot about NO2 and F2 chemistry. I don't even know that. So like typically you'll be given mechanisms, a mechanism or various mechanisms. Let's look at something else though. So this is something that's really confusing. I think is confusing at least. So from the overall reaction, if you're just given the overall reaction, what can we say about the rate for it? We can say that the rate is equal to some rate constant times NO2 raised to some power times F2 raised to some other power. And the sort of the thing that we've been learning this whole time when we look at integrated rate laws and the method of initial rates is that these things cannot be, they're not related to these coefficients up here. And that is still true, but it's true for the overall reaction. So if you only know the overall reaction, we know nothing about what the order of the reaction is. So we don't know what the order of the reaction is. We don't know what the order is for the individual reagents. However, for reaction mechanism, since we know what these fundamental steps are inside of it, so here we don't, at the top, we don't know what the fundamental steps are. So we can't say anything about X and Y. But in this bottom part, we do know what these fundamental steps are. And so we can actually say what X and Y are. So I don't think we've actually discussed exactly what it means for something to be first or second order or third order, what this means other than like, here's how you solve a problem with the integrated rate law or method of initial rates. What these terms actually refer to are how many molecules are involved in that, let's say for the reaction mechanism, in that step. So here we have, because we know the mechanism, we know this is an actual step that's happening. In this step, there are 2 molecules involved in this. And so this thing would be second order. This step 1, would be second order. And we could write out a rate for it and say that the rate here, let's give these numbers, K1 and K2. We could say that the rate for the first one is K1 times NO2 times F2. And we can say that they're both to the first power. So now it's like we're saying the opposite, where we're saying, oh, the coefficients do end up kind of going here. But that's only true for mechanistic steps. So if you know the mechanism, you can say that because we know that truly in step 1, there are 2 molecules involved in the reaction. Super confusing, right? So the short kind of thing is, for mechanistic steps, the coefficients on the reactants can be used to determine the order of the reactants. Is not true for the overall reaction. And what I mean by that is that we cannot say the same thing for this. We can't just write out a rate for this and just plug in 2 and 1 for it. So we could write out a rate for this second one too, which is that the rate is equal to K2 times fluorine times NO2. And again, we know that those are both to the first power because we're not looking at the overall reaction mechanism. I'm sorry, we're not looking at the overall reaction. We're looking at the actual mechanistic steps. But so what you might infer is that since the sum of the reaction's mechanism steps equal the overall reaction, and we can write rate expressions for these individual steps, that there must be some way just to combine these 2 rates into the overall rate law expression for this. And you would be correct in that. So just what I'm saying is just like we sum this up, right, and we can kind of come up with the overall reaction from it, there is a way that's not exactly summing, but there is a way to combine these to figure out the actual rate law expression here. So if you know the reaction mechanism, right, so if we know the reaction mechanism, we know the rate law. So how do we do that? So let me shrink this down a little bit. Yeah, how are we going to write the rate law for this? So an important thing to think about when you're looking at reaction mechanisms is what's called the rate determining step. So, yeah, so this app is kind of wonky in terms of moving stuff. There we go. Put this small over here so I have some room. So the rate determining step, if you look at the chemical reactions and try to understand their definitions and stuff, it gets pretty confusing. But basically, if we step back and don't think about chemistry at all for a second, in any kind of sequential process where things happen in sequence, so like an assembly line or something, the overall rate for the process is determined by the slowest step in the process. So, for example, if you're like, let's say, let's say that you're baking cakes, for example. So if I'm baking a cake, and let's say that I make the batter. This takes me 10 minutes, for example. And then I bake that cake. So now I've got it in my oven. I don't know, oven looks something like that, right? So I've got my cake in there, it's in its cake pan or whatever. But this baking it takes 2 hours. And then like whatever, icing the cake. So now I've got my cake and I ice it. Icing it, let's say, takes 5 minutes. Icing a cake's a pain in the ass, but we're doing a terrible icing job. We're doing it in 5 minutes. Let's say now that you're running a bakery, stay with me on this. Let's say now that we're running a bakery, right? So the number of cakes that we can produce is sort of dependent on this process here. So how long does it take me to make an entire cake? It takes me 2 hours and 15 minutes to make a single cake. If I want to speed this process up to where I can make more cakes or cakes a lot faster, like say I want to make like 10 cakes or something, which part of this process is which part of the process does it make sense to try and speed up, right? So if I want to bake 10 cakes, it's going to take me whatever, 20 hours or something. If I try and speed up the process by making the batter, so if it takes me 10 minutes to make the batter, that doesn't actually help me because the bottleneck here is not in making the batter, it's in baking, right? Baking takes 2 hours. I can, at 10 minutes to make the batter, right? I can make, 12 batches of batter in the 2 hours it takes me to bake the cake. So no matter how much I speed this up, like if I speed this process up and making the batter, let's say down to 1 minute, it doesn't matter because then I'm just still waiting for it to bake, right? If I want to speed the process up, I somehow have to figure out how to speed up this baking part. Another common way that this is explained, Art King, another common way this is explained, let's see, I think it's like a literal, how did my prof explain it to me? It's like, if you look at like a funnel, and I'm pouring a liquid into it. So yeah, I'm pouring some liquid and it's kind of getting into the funnel. And it streams out at the bottom. what's the rate determining step here? It's the amount of time that it takes for it to travel through here. So like if you're trying to push something through a funnel and I'm dumping it into the funnel, the speed at which I dump it into the funnel doesn't really matter very much, right? If I get like if I'm trying to pour oil into my engine or something, and I'm pouring the oil in and I get impatient and just pour it faster, it doesn't actually really speed this up at all, because ultimately this thing is going to be dependent on this bottleneck here. And I've had this experience where you pour it too fast and then it overflows outside of the funnel. So the rate of a process is sort of just, the takeaway is just the rate of a process is just dependent on the slowest step that you have in the overall process. So if you were designing like an assembly line or anything, this would always be true. If you want to speed a process up and it happens in sequence, you have to speed up the slowest step. And so that is true of chemical reactions as well. So even though the mechanisms can get reasonably complex, this one's only 2 steps, ultimately, the overall rate of the reaction that you observe ends up only depending on this actual step here. So the slow step, whatever our slow step is, we call that the rate determining step. That's not how you spell determining. Determining step is the slowest step. And as the name implies, rate determining step, it is it will accurately describe the rate law. So the rate determining step is the slowest step, and I think that's a reasonable way to say it. It describes the rate law. So whatever you observe for the rate law, which tells you the rate of the reaction, is going to just be determined by the slowest step in the reaction. So I've got 2 rates here. What's the rate law for this? We just need to worry about the one that's for the slowest step. And so our rate law for this actually turns out to be the overall rate law for this just turns out to be the rate that we wrote for this first step in the mechanism. And you'll note that the exponents on here don't have anything to do with these. They have to do with this. So if you know the mechanism, you can write the rate law for the reaction. You just write out the rate law essentially for the slowest step in the mechanism. This is a simpler case of kind of how to do this for reaction mechanisms. So no matter how many steps you had, if this was a 20-step mechanism, let's say, like say that there wasn't just step 2, there was step 3, step 4, step 5, step 6, all this crap. Once you recognize which one is the slowest, assuming that there's nothing else weird going on, you can write out a rate expression for that, and that will allow you to get the rate law for the overall reaction. Yeah, so in this case, K1 would be the same as K. And a lot of times we just, we'll get to kind of what kind of gets weird with K. You know which one is the slow step. So things you don't have to do. You never have to, you'll never have to say, like, write out an actual mechanism by looking at the overall reaction. They'll never say, here's the overall reaction, just write out a mechanism from looking at it. So like, actually having to write out these steps from your brain. We do that in organic chemistry, but we don't do that in this class. You'll also never have to guess which is the slow and fast step. We should probably teach kids how to do that. Just kids, you guys aren't really kids. We should teach you guys how to do slow and fast steps in organic, but we don't really do that either. But so yeah, so you don't have to worry about this. This is stuff that's given to you typically, and you're trying to figure out how to get the rate law from it. That's generally how this stuff looks. Okay, so the key thing, if all of this didn't make sense, or if very little of this made sense to you, because you wherever you are in your studies. The key thing to recognize here is that this thing here with the exponents, it's only true for mechanistic steps. If I have a mechanistic step, I know the exponents on these things, on the different reactants. If it's not a mechanistic step, it's an overall reactant, I don't know that. It can feel the same sometimes, I think, for students, but it's not. All right. Let's look at this other scenario, or this other situation. So I guess there's a couple of things that are, well, it's probably better to work it out with an example. So the rate law, one thing you'll notice is the rate law, we can have intermediates here, like for example, this fluorine atom. That doesn't actually appear inside of the overall reaction. It cancels out. That's really what it means for it to be an intermediate, right? It's something that appears along the way, but that we don't actually observe in the final product. So you'll notice there's no fluorine over here. It's just something that pops up. So it's kind of like when you're traveling between Austin and Houston, if you stop at Buc-ee's along the way, right? That's not really where you end up. So Buc-ee's would be kind of like this intermediate that you stop at. Okay, so for the rate law, the intermediate should not appear in the rate law. The rate law should only have either the products, more often the reactants, but should only have reactants and products in it. So let's look at this example. So ozone, which is a pollutant, well, it's a pollutant close to the surface of the planet. When you get to the upper part, we need it. But anyway, ozone will break down into oxygen. So we're looking at these two allotropes of oxygen here. Ozone will break down into O2. This is the overall reaction. The mechanism for this looks like this. So step one is whatever ozone breaks down into oxygen, or O2 plus this other oxygen atom that's just sort of by its lonesome. Monatomic oxygen, I guess you could call it. And then in step two, we end up forming O2. So this is an intermediate. And then, this is our reactant and this is our product. You can kind of do it in your head that this adds up to be the overall reaction here. But so the weird thing here, the new thing, is that we have now introduced these equilibrium arrows. Sorry, I just read the book. He's coming in. The weird thing here is that we have an equilibrium arrows here, and we can see that there's a K1 going in one direction and a K -1 going in the opposite direction. So if the equilibrium appears, we assume, you can always assume that the equilibria is very fast. So equilibria, if there's equilibrium arrows, that means that the equilibrium is established extremely fast. That means the equilibrium is established extremely fast. And so that would make this our slow step. And so we want to write out a rate expression for it. So we're going to do it the same way that we did in the last one. So we say, okay, well, that's our slow step. We want to write out the rate law for it. We want to write out the rate expression for this reaction. We know that the rate of the overall reaction is only going to depend on the slow step. So I'm going to write that out. And again, because these are fundamental steps in the mechanism, I know that the exponents on here are just going to be related to these coefficients here. So I've written that out. We can write out K2 out front of it. And so the problem with this is the rate law. Like when you actually write out a rate law, it can't have an intermediate in it. we don't want to write out a rate law for the overall reaction with an intermediate in it. And there's a bunch of reasons for that, but just take it as a rule. And so we have to figure out a way to get rid of that. So we need to replace oxygen, this monatomic oxygen. And so the way that we do that is we want to write out, so you can take, so if in an equilibrium, one way to think of equilibrium is that you hit a point where the forward reaction and the reverse reaction are happening at the same rate. Yeah, it tells you what the slow step is. Or if it has an equilibrium step, you assume the equilibrium is fast. But so in an equilibrium process, the forward and reverse reaction have the same rate. And that is the key to getting rid of these intermediates. So if we know that, let's see, so if we know that this forward rate and this reverse rate are the same, then we can say that K1 times O3, so that's the rate for the forward reaction, we can set that equal to the rate for the reverse reaction. So we're saying that these two are equal to one another. Let me put some numbers out here. So that's the rate associated with 2. And then so all I'm saying here in this, the reason I'm able to set these two things equal to one another is because we're saying that they're in equilibrium. And so this kind of rate associated with 1 is equal to both of those. And so the rate is the same, so I can set them equal. And then in order to get rid of this oxygen that's here in what we know is actually what defines the rate of the reaction, all we have to do is solve for oxygen over here. So we solve for oxygen, and what we end up with is oxygen is going to be equal to what? K1 times O3 divided by K inverse 1 or negative 1 or whatever times O2. And then we can just substitute that back in. So what you'll notice though is that once we solve for this, right, this has O3 and O2 in it. O3 and O2 do appear in the overall reaction, and so you're golden. That's all we're trying to do here. This part here we can use to get rid of intermediate in the rate expression and actually derive a rate law that makes some sense experimentally. So rate then would be equal to, so now I'm going to substitute in so now I'm just going to take this over here and I'm going to substitute it in. And what I'm going to end up with is K2 times K1 over K negative 1 times O3 over O2. Yeah, hold on, let me make this look a little cleaner. It's kind of a mess. So we can substitute that in, we can put it in brackets. You say K1 over K negative 1 times the original O3. And then we can simplify this down. And so we can just say rate. You don't have to put the 2 subscript on there. That's just me trying to allow you to figure out which rates I'm talking about where. But so we can take and we can combine O3 together to make O3 squared. I think that's pretty clear. Less clear is probably that you take all of these K values, K2, K1, K minus 1, that's what ultimately becomes K for the reaction. We just call that K. Sometimes you'll see it with KOBS written on it, meaning K observed. That's the actual rate constant that you observe for the reaction. So we're combining all of those, and then we're just saying that that's our rate law. And so K is equal to K2 times K1 over K minus 1. And so that's how you deal with getting rid of intermediates. So this whole process like that we've done here, the whole point of it is, or sort of the only thing that's different from the last one that we did where we just wrote it out, the rate for the slow step, is that we have an intermediate that appears inside of the rate expression that describes the slow step. And so this whole process that we went through here, all of this is just to get rid of that intermediate. So we're just trying to get rid of an intermediate. So we identify the intermediate because it doesn't appear in the final product. So it's something that appears inside of the reaction steps, or like in the mechanistic steps that we don't see appearing over here in the products. And since when we write out the rate expression for the slow step, which is the rate for the overall, which ends up being the rate for the overall reaction, if it contains that intermediate, we have to get rid of that. And so we do that when you have an equilibrium like this. We do that by taking this equilibrium here and recognizing that the forward and the reverse reaction are the same rate. And so we can set those equal to each other and solve for the intermediate in terms of things that actually appear in the overall reaction and just use substitution to get rid of it. And that allows us to derive a rate law allows us to derive a rate law that is actually expressed in terms of the overall reaction. I get the O2 out of the bottom. Did I mess up? Oh, over here you mean? Oh yeah, did I? What did I do there? Yeah, that was that. Yeah, that's just me making a mistake. Thank you. I'm glad you caught that. Yeah, the oxygen concentration doesn't magically float up into the numerator there. Yeah, so this rate law is a little bit weird in that it's weird for a couple of reasons. One is the product appears in it. That's unusual. It's not really that unusual, but it's not something we've really seen. We usually write it in terms of reactants, and one of them appears in the denominator. This whole process is how to get to the rate law. So you write out the steps are write out the rate for the slowest step, and then if you have an intermediate, you want to figure out a way to get rid of that intermediate in that rate expression that you write out for the slowest step, and that's what this whole process is that we went through. And then why does O2 appear in the bottom? Because I made a mistake. So. Okay. Let's see. 943. Let's look at one more. Let's look at another one that's sort of complicated, or I don't know. Yeah, just one more, because these take a little while to get a rhythm for. So let's say that you're given the overall reaction. I'm just going to leave the states off because who cares? This is a reaction that we learn in organic chemistry. Let's see. So this is your overall reaction, and then our steps are, our mechanistic steps are this. And so this first step, this is a fast equilibrium, so it reaches equilibrium extremely fast. This is our slow step, and then this step is fast as well. And we want to write out a rate law for this. What's Arrhenius' law? We have you, is there for the Arrhenius law, do we have you pop it out with equations on that? K equals A times e to the whatever. We'll probably skip that if so. If we do go over that, we'll go over it on Monday. But more than likely for the other stuff, the remaining stuff, it'll probably mostly be qualitative. I try not to lump any quantitative stuff in unless it's like a simple thing on the Monday before the exams. Okay, so yeah, if we want to write out the rate law for this, how do we do it? We just do the same exact thing that we've been doing. So you take the slow step, which is this, and we write out the rate for it. Same thing, because it's a mechanistic step. I know these coefficients just go right here, but we have that same problem that we had in the last one, which is this, that if we look up here, if we look at our rate law, we see CHCl3, that's fine, that's one of our reactants, that's what we want to see, but then we see this Cl, then we see this Cl here, and that does not appear in the products or the reactants, and then we note that it's just an intermediate. Appears here and appears here and appears here, and then it doesn't, we can't see it in the products or the reactants, and so we need to fix that. And so we just do the exact same thing that we just did. So we say, okay, I'm going to come up here, I'm going to look at this equilibrium. I'm going to look at our equilibrium over here, and I'm just going to write an expression for that. I'm going to say that the rate, actually I'll just write it out this way. We're going to say that Cl2 times K1 is equal to K inverse 1 times Cl squared. And then we just want to solve for Cl. And so see it, this, you end up with this kind of weird expression here. Where you actually have a square root for one of the concentrations. But then we can take this and we can just substitute this back in over here, right? And that allows us to write out our rate law, which would be K2 times K1 over K negative 1. So let me write that out in a second. Cl2 to the 1/2 times CHCl3. And we collapse all of these rate constants into K. So we'd say that the rate law for this would just be equal to K times Cl2 to the 1/2 times CHCl3. Yeah, so that's a good question. So Tucker's asking if chloroform, CHCl3, which is chloroform, is on the product side, would that matter? Like, will we have to do anything about it? And the answer is no. So if we come back up and look at the ozone situation that we dealt with over here, we have oxygen that's appearing in the product here, and oxygen appears inside of our final rate law, and that's fine. You just don't want intermediates in there. And so I'll spend the last minute kind of explaining why that is. So this is the overall process. This is the kind of the machinery for solving these problems. It's being able to pick the slow step, which is more or less giving you right at the rate for it, and then do this substitution to derive sort of the overall rate law. There's a lot of different ways that you can ask that question, the question around this, but that's sort of the main machinery of kind of how you'll solve the problems. just very quickly, why do we care that the rate law is actually written in terms of the products and the reactants? The reason is, if you go back and you sort of look at the stuff that we've done, right? The rate law, the way that this works in reality is, like, if you saw this reaction and you're a chemist, you would propose a mechanism. You'd say, I think this is what the mechanism is based on my chemical intuition, as a, and then I could go and test this, let's say, by experimentally determining what the rate law is. And then we could compare the experimentally determined rate law to the rate law that we derive from the mechanism. And so, so the reason that the intermediate can't be in the final rate law is that I have no way to experimentally access that. K1 over K minus 1 is just wrapped up into K now. We just call that K. So these all end up getting combined into just what we call K. That's what we actually see as the rate constant for the reaction, even though it's actually the combination of all of these. But yeah, if I want to run experiments on this reaction, what can I control? If you look at the method of initial rates, we're looking at the concentration of the reactants, and we're changing the concentration of the reactants and seeing their effect on the rate. If I look at the integrated rate law, I'm plotting the reactant concentration as a function of time. We have no way to see the intermediate in the reaction, so we have no way to access that experimentally, so you can't actually test this. If they were like, go and test this using the method of initial rates, that would be complicated to do because this is an intermediate. So that's at least one reason why you always write the rate law out in terms of the products and reactants. The square root comes from, where did I even go through that? I think I just skipped ahead but so this is squared. And so after I do all my algebra, I bring K1 over K minus 1. So I bring this over here. I have to just take the square root of everything on that side. That's where that comes from. So instead of writing it as like, the big square root sign, I write it as 1/2 because that's the that's how it ultimately appears in sort of the rate law. So this, this reaction is half order in chlorine, which is, I don't know, that's not something we see with the other types of rate stuff we work with. Yeah, I'm not saying 100% we won't go over quantitative Arrhenius stuff. If we do, it's not so bad. Like it's a very like, I've got a bunch of numbers, let me plug them into the equation. And I don't know, maybe it's just because I'm not a physical chemist. I don't really care that much about that. What we will definitely what I do want to go over is, I'm much more interested in your ability to be able to read reaction diagrams. So if you've got reactants, I've got A and I'm going to B over here. I want you to be able to what does this up here mean? What's the difference between this and this? So describing these are really kind of crucial for chemists. The Arrhenius laws, it just describes the activation energy quantitatively, just not, I don't know, I guess it's important, but it's not it's crucial as kind of understanding these things conceptually. So anyway, this takes us through reaction mechanisms. So far what we've done is we've done method of initial rates, integrated rate laws. Those are kind of the key quantitative components for the exam. And now we've looked at these reaction mechanism things that are kind of the final thing related to rate law that is meant to tie it all together. Canvas says this includes 2 more chapters, really. This will have solubility. Yeah, it'll have solubility in kinetics. I don't know what other chapters it says on the Canvas homepage. I'll have to take a look at that. But yeah, I think what you're saying is correct. It'll have the stuff that's from the GChem website. Yes, and the past lectures will go up on YouTube right away. I apologize if those weren't up sooner. So yeah, so right after class, okay, no, I'm not messing with, so the nuclear chemistry, you have to know the half-lives for, that's the only thing we'll do with nuclear chemistry. And I'm not messing with inorganic chemistry at all. We probably won't mess with that at all this semester. Most of you guys aren't going to take inorganic, so I don't really care if you know about it or not. I'm not an organic chemist. I mean, I do some, but yep. So yeah, so kinetics and solubility, I'll go in and like, I'll make a note about that in an announcement. Let me make a note so I don't forget to make that announcement. But yeah, that's pretty much it. Exam on Wednesday. We'll post more information just like we do for the normal exams for our other 2 exams. So similar kind of stuff. We'll give you lots of information about it as it approaches. But you guys have a nice weekend. Try to find some time to relax in between your studying, and enjoy the nice weather, and try to stay safe out there. Bye, you guys.